Okay, so welcome everyone to the Maui Institute for Astronomy. I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist. I'm not sure that anyone really quite knows what my title means, but so if you figure it out, let me know. But I do know that one of the things I do is I put together these public talks, and so I think we're just going to go ahead and get into it. So here's the idea is that we're going to go through and kind of look through telescopes and see what the universe looks like. So, and I've kind of made this a spoof on Fodor's Guide. Everyone knows Fodor's Guide, yeah. That was the trick to get you all in the doors. Now, the real truth is, you know how your friends come back from vacation and they show you those long, boring slideshows? That's what this really is. Okay. There are a lot of images in here that were taken with the Las Cumbres Observatory Global Telescope Network. You'll see the little logo down here, the credits down here, along with someone that was there, at least somebody that was there when they were taken. And first thing I want to talk about is space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's the long way down to the road to the chemist, but that's just peanuts compared to space. So, one of my friends at Caltech can just quote that, just ramble that off really good. I'm not there yet. I've got to learn it. All right. So, when we talk about astronomy, one thing that we generally forget is we forget about the sun. And I actually started off kind of as a solar physicist, doing solar astronomy. And so, don't mind me, I'm just taking a picture of everyone here. Blackmail for later. Yeah. So the sun. And this is actually from the SOHO satellite. It's actually not a terrestrial image. But you can see sunspots here in the granulation. And this is the color of the image that I got from from SOHO. This is, unadulterated color. Now, does anyone believe this color? Yes. Some of you know me well enough to know that I preach that the sun is white. Okay? This is far too yellow to be the sun. And you know how you prove that? Well, you don't look at the sun. That's not a good idea. Yeah, but that's a very good idea. You can wear the eclipse glasses. But the problem with the eclipse glasses is, are the eclipse glasses white, or do they change the color of the light coming through them? So here's the way that I suggest that you can tell what color the sun is. Okay? Take a white piece of paper, go outside, get it in the sunlight, and look at it and tell me what color it looks like it is. What color does a white piece of paper look like out in the sun? White. Okay. So this is what I did. Yeah, this is roughly the correct color for the sun. Roughly. And I'll show you in a minute how I calculated this. It's not perfect. It's a long way from perfect, and color rendition, color vision is quite difficult at best. So what I did is, there are 3 types of cells in our eyes that detect color. There are 4 types of cells that detect light. 3 of them help us distinguish different colors. There are cells that detect red, so that's this line. There are cells that detect green, and cells that detect blue. Okay? And this graph is showing how responsive our eyes are to the red, green, and blue light. So in other words, our eyes really see this color of light very well. Okay? But this color, it's not so good in blue, it's not so good in green or red. And what I did is I took just where the peak of each of these is. And then I got this this spectrum from the Stanford Solar Center, and I looked at the same wavelength as the peak, and I kind of estimated how bright the light is at that color for the sun. That's how I did this. It's probably, it could be a long way from truth, but okay. So here's the actual color of the sun. Here's white. Here's the sun. It's kind of hard to tell because you've got all that granulation. So let me put another. That's about the difference, approximately. This is the sun. This is white. This is white as a reference. Because without that white as a reference, it's really hard to tell that there's any color to it. Okay? All right, everyone follow? And then, of course, I'm looking at this up here, and I look on my screen down here, and the contrast is much better on this screen than on my screen down there. So really be warned that color perception is very subjective. If you look at something red near something blue, it looks redder. You know, the contrast, what things are around it, do flavor how your mind perceive the color. Okay, so there's just those two. You can definitely see the color difference. I was doing that because it was actually kind of hard to see on the monitor. So here's why I'm gonna start off with that is the color of astronomical images is often enhanced. So in other words, if it's just a little bit greenish, they'll really increase the green. And there's one image in particular when some of the amateur astronomers, when I hit the Orion Nebula, don't forget to let me talk about that. All right. Well, standing room only. People got lost, didn't you? This is not the Maui Arts and Cultural Center. You all right? Okay. You were looking for whatever band is playing tonight. Ooh, you missed. Okay, so the sun. Let's go back to the sun. All right. This is sort of the interior of the sun. First of all, the sun is a star. Now, what is a star? Go for it. Something that'd be hot or cold in space? No, that's not good. Yeah, go for the hot end. Yeah? Yes. A ball of energy and gas. We're getting a little closer. Okay. Aaron, I know you know. That's a pretty good definition. So it's a large ball of plasma. No, because the sun is a star. It's a large ball of plasma held together by gravity, and the gravity and temperature is high enough that there is fusion in the core, in the center of the star, or not necessarily exactly in the center. So there are some cases where you'll have a shell with fusion going on. And we also consider a white dwarf a star, even though the fusion has stopped. It used to have fusion in there. But just the sun is a star, and so by star we mean something that energy is generated by fusion. Okay? The sun is a main sequence star. What we mean by a main sequence star is it's fusing hydrogen into helium at the core. That's a main sequence. You can fuse other elements and start forming carbon and oxygen and silicon and iron, all the different stuff. But in our sun, hydrogen is forming in helium. The sun is a middle-sized star. Everyone's heard that, right? Okay. Stars range from about 8% of the mass of the sun to about 100 times the mass of the sun. It's a middle-sized star? Somebody explain this to me. I never got this. 8% to 100 times. Yeah. So how is that a middle-sized star? On order of magnitude. Yeah, on order of magnitude. That's but even then it kind of misses, doesn't it? Okay. I don't know what weighting they're using. Go ahead. Geometric mean? No. So so yeah, let's round this to 0.1 and then shift the entire scale. So stars range from 1, the sun is at 10, and the biggest is at 1,000.
Well, I think that if it was more middle of the magnitude scale, it would be 10 times.
Yeah, it kind of misses on the on a logarithmic scale. It kind of misses on that. That better? Oh, question. Oh, repeat the question. Thank you. Yeah. So we're just kibitzing over how this works, and if anyone in the audience out there knows how to do this,
So we don't want to call it a dwarf?
well.
Because you get
Well, it's not even it's not that it's a dwarf. A dwarf star is sort of up to maybe half the mass of the sun. I don't know, but yeah, I mean there might be some weighted mean that we could do, but anyway, okay, we've beaten this to death. We've beaten this to death. It's No, we're not going to do a t-test on this. That was the suggestion. So, the sun is about 4.6 billion years old, and it's going to live to be about 10 billion. But another, million years, billion years, we don't want to be here anyway. So, the sun is made of about 73% hydrogen, 25% helium, and then there's heavier elements. Okay, so carbon. Just a minute. Check. All right. How about now? Okay, I must have bumped it. All right. Sorry about that for the virtual audience. So the sun is made of about 73% hydrogen, 25% helium, and then a bunch of the heavier elements. So the reason that we always talk about this number is the universe started out as about 75% hydrogen, 25% helium. So you'll notice that the sun is made of mostly stuff that was around when the universe was formed. Only a little bit of other stuff. So the carbon and oxygen and silicon. And space junk. Yes, exactly. Okay, the sun is about 108 times the diameter of the Earth. So over 1 million Earths would fit inside of it. Okay, the distance between us and the Earth, or between the sun and the Earth, is about 214 times the diameter of the sun. So everyone sees the sun up there, right? Did anyone notice the Earth up there? There's a little dot in the lower left corner. And I've very carefully done that to scale. That's the Earth compared to the sun. You see the little blue dot? Okay. And so let's scale this so we can fit the distance between the sun and the Earth. There you go. Okay. So again, space is big. Yes. Mm-hmm. Yeah. Okay, so the question is, the sun is a very large object, and where do we measure the distance from the Earth to the sun, correct? I would imagine it's probably through the center of the sun. Okay. The center of the sun. Does the distance between the Earth and the sun change during the seasons? Yes, actually, in round about December is when we're closest to the sun. But of course, the seasons are not caused by how close we are to the sun. It's caused by the tilt of the Earth. So, yeah, the orbit of the Earth is an ellipse. And so if you want to check on Wikipedia, and for all you teachers out there, quickly cover your students' ears because I'm going to say that Wikipedia is good. All right? So Wikipedia is actually a very good reference in general, is what I've found. And so go look at Kepler's laws. That's a great start for all of that. All right. Now let's talk about the moon. I was asked a while ago, well, what's the name of the moon? It's actually Luna. Yeah. And they looked at me and said, well, no, because Luna is lunar, that's moon. Well, no, our moon is Luna. Not all moons are Luna. Okay. The definition of a moon is a natural satellite of a planet. Okay, so actually the Earth has lots of moons. This is the one you see at night. Okay, so we started off with the brightest thing in the sky, which is the sun. This is the next brightest thing in the sky, which, the moon. And our moon is made of silica, so like rock. Okay. Quartz, quartz is a good example. Alumina and lime. Those are the main components of the moon. There is a core that they think has some iron in it. Yes? Do you have a question? Or yes. Yeah, you just looked like you had a question. Okay. Okay. So it's made of silica, alumina, and lime. The composition of the moon is very similar to the Earth. In fact, so similar it's kind of disturbing. The isotopic abundances of the Earth and the moon are almost identical. And they're distinct from any other body in the solar system that we're seeing. So the idea is that the Earth and the moon really were originally one thing, and that something hit the Earth hard enough that it splashed basically the moon up into orbit around the Earth. Just scooped off a chunk of the Earth. Yes? Isotopic abundances, can I define that? Yeah, there are different types of, say, hydrogen. Have you heard of heavy hydrogen? Okay. Or heavy water, maybe? So there you can have deuterium, which is heavy hydrogen. Deuterium is, regular hydrogen has one proton in the atom and one electron orbiting, right? Deuterium has one proton, so same number of protons, and it also has one neutron in the nucleus. So neutrons are neutral charge. You can add them for free without changing the element, the way the element acts, but it's heavier. It's much heavier. And so the isotopes are same charge, same number of protons, different number of neutrons. So how many helium atoms there are compared to deuterium is the same for the Earth and the moon. And oxygen, carbon, there are different isotopes with different numbers of neutrons in the nucleus, and that it's almost identical between the Earth and the moon. Yes. Is there any validity to the theory that the mass of the moon came from the Pacific Ocean region? No, the Earth was hit hard enough that it liquefied effectively again. So it re-liquefied. And then that mass was basically just splashed off, and the Earth kind of formed into round again. I think you were next, and I'll get to you. So the question is, there's a comment, I've heard that comment too, that the Earth and the moon, you could consider us a double planet. And is there criteria for that? If there is, I don't know. Yeah. You had a question? That's a very good question, right? So her question is, if the moon was knocked off of the Earth, then why doesn't the moon have water on it? Okay. The water, we think the water came after the Earth cooled off quite a bit, because water that came to the Earth before then would have been broken up, and we would have lost the hydrogen, and we would have just kept the oxygen. The moon, however, if you went to the moon with a block of ice right now and put it on the surface of the moon, do you know what would happen? It would, go ahead.
It would, because there's no pressure pushing down on it,
Mm-hmm.
it would actually just instantly turn from a solid to the gas.
Yes. Yeah, so it would the block of ice would turn from a solid to a gas. It would sublimate, okay? And just putting it out anywhere on the moon. And that gas, the moon doesn't have enough gravity to hold that gas, so that gas would escape out into space. So if we had water on the moon now, unless it's in a very shadowed spot or somehow protected from the heat of the sun, it would evaporate. And we actually do think that there's water on the moon in some of the craters. Okay. All right. One more question then. Let's move on. Yeah. Mm-hmm. So the question is that the part of the heat comes from radioactive decay from the elements in the interior of the Earth. Why isn't the moon kept warm from that, from a similar process? And I think that part of the answer is, and Stan will correct me if I'm wrong, it looks like you know this. So part of it is most of the decay has turned way down. So early when the Earth formed, the decays were enough that it actually did have an effect, and that's one of the explanations of what's called the faint young sun problem. The sun was too faint to keep the Earth as warm as we saw. But now the elements that decay enough to really give us heat, they have decayed already. Mm-hmm. Yeah. Yeah. So the addition that Stan Truitt just gave us was there is still some there, but it's such a small amount that the surface of the moon allows it to escape fairly effectively. All right. So, now here's something fun about the moon. Does everyone know that the same side of the moon always faces the Earth? It does. So the comment was, I thought it rotated. The moon does rotate. It rotates at the same rate it orbits. Okay? So we know that the moon orbits around the Earth, and so my controller here, it is rotating. It's rotating at the same rate it's moving around me. It takes the same time, and these are actual images taken of the moon here from the Earth, and you'll notice, okay, this crater is still in the same place all the time. That same one crater is in the same place all the time. Yeah. Well, actually, he's right on this one. So the question was, even though it's rotating, we don't see the dark side of the moon. And Stan is thinking of in terms of illumination and is saying, no, you do get to see the dark side of the moon. There's the dark side of the moon. But really, the term the dark side of the moon is from the Apollo missions when we were trying to when we needed to have radio contact with the Apollo missions. When they went to the far side of the moon, they went radio dark. That's where the dark side of the moon, the term dark side of the moon comes from. At least that's what I've been told by someone that I think would know. You know, yeah, Pink Floyd, exactly. Okay. And another thing that we ought to know about the moon is it goes through these things called phases. Does anyone know what causes the phases? Yes. Go ahead. Okay, yeah, so the guess is that maybe the shadow of the Earth is blocking light from the moon. That's not correct, but good guess. We like that guess. Yeah, that's what's called an eclipse. Yeah. Yeah, you've got the right idea. Let me go to the next slide, and I'll kind of repeat what he just said. So, as the moon orbits the Earth, we see. So when the moon is on the same side as the sun, we see the dark side because the light side is always towards the sun. When the moon is over here, we see the entire light side. Okay, when it's here, we see half of the light side, half of the dark side. And when it's here, we see half of the light side and half the dark side. So think about looking towards the moon. Which half of the moon do you see? Okay. Yes. Right. Right. So the question is how is it that the moon seems to rise in the east, set in the west, but it's actually going the other way? Well, the Earth is spinning faster, goes around faster than the moon orbits the Earth, and so the rotation of the Earth is what dominates what we see. That's what causes what we call the sun rising and setting, and the moon rising and setting, and even the stars rising and setting. Right. The ratio between how fast the Earth spins around and how fast the moon orbits, that's just basically a lunar cycle. How many days there are in a lunar cycle. That's correct. Okay. Okay, now here's something fun. Oh, did you have a... Mm-hmm. Okay, the question is, the sun has all the planets orbiting around it. Does the moon orbit around the Earth like the planets orbit around the sun? Is that a correct? Yes, exactly. Yes. Yes, the Earth does the same thing to the moon that the sun does towards the planets. Okay? What happens is there's gravity. Okay? I'm noticing gravity right now. That's why the moon orbits the Earth. And that's also why the Earth orbits the sun. We'll have to talk about gravity sometime. All right. Yeah. The comment for the virtual audience was that gravity is a heavy subject. That's good. Okay, now everyone knows the moon's quite bright, right? No, it's quite dark. About 13% of the light is scattered back out by the surface of the moon. Okay? That's comparable to weathered asphalt. So next time you're in a parking lot, look down at the surface of the moon. All right? And this is a picture of one of the astronauts on the moon. You'll notice it is quite dark. You'll notice on his suit, on his knees, there's some dark material there. That's dust from the moon. The moon is very, very dark. It's trying to make itself hard to see, I guess. All right. And so, pardon? Yes, there is no visitors bureau. They don't make a lot of money on tourism, I guess. Yes. So if it was not so dark, if it was more reflective, what would be the implications on the Earth? Astronomers would be very unhappy with full moons. We're already unhappy about full moons, but we'd be very unhappy. Full moons would be quite bright. I mean, let's say you double the amount of light scattered by the moon on a full night of a full moon, you'd have nearly double the amount of light. During the day, it would be easier to see the moon when the moon's up. All right. And here's another good example. And if we have any questions on this particular image, Dr. Gary Greenberg is the one that took this image. It's right in the back here. And these are true colors, aren't they? So these are very quite genuine, accurate colors, and you can see, and this is dust from the moon. This was obtained from a sample from Apollo 11, is that right? Yeah, from Apollo 11. These grains, you can see, are quite dark. There's a couple of lighter colored ones. The moon is really surprisingly dark. All right. Another question? Yes, that is exactly correct. This is what he was saying was this is a picture of dust grains from the moon. So they actually picked up dust in the moon from the moon when they were out there, brought it back here, and Dr. Greenberg put it in his microscope and took a picture through the microscope of the dust. Yes.
Will we be getting one of weathered asphalt as well?
Pardon?
Will we be getting one of weathered asphalt as well?
Yeah, there we go. Have you taken any pictures of weathered asphalt through the microscope? So Dr. Greenberg's response is that no, he has not, but he needs to try that. Aaron, trust me, I know this guy. He'll do it. Yeah. Okay, let's do one last question. Yeah. Yeah. Okay, the question is the speed of the moon around the Earth. That's pretty easy to figure out. Okay, it's just gravity and then centripetal acceleration, basically. So the rest of the question is, what about the speed of the Earth around the Sun? I was actually calculating that a while ago. I can't remember the numbers. It's a comparably easy calculation in principle. You go in and you calculate how strong the gravity is from the Sun, and then you know that that's equal to centripetal acceleration. 2 pi 93 million miles per year. Yeah, so the radius is from the Earth to the Sun is 93 million miles. So the circumference of a circle, and the Earth's orbit is pretty close to a circle. Well, 2 pi times the radius, which is 93 million miles. Okay, and that's how far we travel in 1 year, and we can calculate that rather quickly. So the calculation that you did was about 67,000 miles an hour, and Stan is saying that sounds about right. I don't even remember. If I really need it, I'll sit down and calculate it, or I'll look it up. But yeah, 67,000 miles an hour. That sounds reasonable. Yes. Yeah. So, well, the question is, how does this 13% compare to the Earth? On average, the Earth is quite a bit brighter because remember, the oceans reflect a lot more light, and snow is very bright. It reflects a large fraction of the light. Anyone here know the albedo of the Earth right off? The average albedo? Everyone's shaking their head. We don't know the numbers right off, but the Earth is actually brighter than the Moon. Okay? So planets. We're only going to go to a couple planets here. So planets are stars that wander, and the definition of a planet, I grabbed this. Okay? A planet is in orbit around the sun. Okay? So a large object orbiting another star is not a planet because it's not around the sun. It has a sufficient mass to assume hydrostatic equilibrium. In other words, it makes itself round. So the Earth orbits the sun. It's round because of its gravity and mass put together, squishes it round. So far we're a planet. And it has cleared the neighborhood around its orbit. So there's not a lot of other things in the same orbit as the planet, because they've all been swept up, presumably, by the gravity of the planet sucking these things in. And this is the definition that excluded Pluto. So I'll let you decide whether it's a good one or a bad one. I'm not going to get into that. I think Pluto's a comet. So, all right. So let's go ahead and first talk about Venus. Venus is the evening star or the morning star. Yeah. So let's go back. This is okay. This is this image that I took here. That's actually from Stellarium. It's a free online program. If you don't know it, it's the second best free way to look at the sky. The best free way to go look at the sky is to go outside. Put down your computer and go outside, people. Okay, but this is actually a pretty nice program for free, and so this is Venus in the morning because it's rising. It's got to be fairly close to the sun. So and this is I think a couple days ago. Is the Venus would be rising in the morning, and it kind of looks vaguely like that. It looks like a bright star. Looks like a very, very bright star if you look at it. Okay, if you look at it through a telescope, this is about what you would get. And so this was one of the astronomy pictures of the day. Go ahead and take a look for that. And Venus is a rocky planet, and it's considered to be the planet that is most similar to Earth. It's got about the same mass, about the same radius, the same density, but it's also the hottest planet in the solar system. So little Mercury that's in there right next to the sun isn't even as hot as Venus. Yep, really. The reason is it's got a very thick atmosphere. It's got a runaway greenhouse effect. It's got this incredibly thick atmosphere. The sunlight comes in, heats up the planet, and then the infrared radiation that is radiated can't get through the clouds. Okay? And Venus also goes through phases the same way the moon does, and that was playing a moment ago, but apparently it wanted to stop. Let me show you how it goes through phases. So here's the sun, and remember, Venus is a ball; it's a sphere. So when it's on the far side of the sphere, or far side of the sun, we see the lit up side of Venus, right? And then over here, a little less, a little less, a little less. Here, the light is traveling. So the way this is we're looking this way, and then at the same distance of the sun and off to the left, that's Venus. Or off to the right, that's Venus. And so we see about half of Venus lit up. Did you know that Venus went through phases like the moon does? Yeah. Oh, he needs a telescope. Do you need a telescope? We should find you a telescope. Okay. So Venus, and notice that it gets larger when it's closer to a new phase, when we're seeing the dark side, because the illuminated side is on the far side of Venus. Yeah. No, when it's closest to us, it is not. The question is, when is it brightest? It's not going to be when it's closest to us. Yeah, that's going to be the darkest because there's just nothing lit. We don't see much of anything lit up. But yeah, it's probably I would say somewhere in about here is where it would be brightest. Yeah. You just kind of look at the area that is illuminated. Yeah. Well, if you're using angular area, you don't have to factor in the distance. So I'm looking at the angular area squared, or the angular area of what's illuminated. That looks like it's the largest angular area of any of them. That's how I would quickly calculate that. Okay. So Stan and I are don't mind us. Stan and I are going to debate which way to calculate this, but we're both basically doing the same thing. We've got the same mathematics. Yeah.
There's a psychic in Las Vegas who would predict an outbreak of UFO reports and to watch for them. And he'd be telling people to look for Venus at its brightest. And people would phone in, I saw the UFO, yes.
Okay, so the comment is there is a psychic in Las Vegas that would predict outbursts of UFO sightings, and what the psychic would do would say, look for when Venus is at its brightest.
He wouldn't tell him that.
Oh, he wouldn't tell him that.
He'd just say, look out there in the evening.
Oh, okay, so he would say, go out and look on this night for the UFO, and it happened to be the night that Venus was the brightest. So the people would go out and look, and they'd see Venus, and they'd call him and say, I saw the UFO. Got it. Yeah. That sounds, yeah. Everyone here, remember, you can see the moon during the day. The moon is the most commonly reported unidentified flying object. Friend of mine whose stepfather is a professional astronomer called me one day. And she said, JD, there's this very bright thing in the sky. That's the moon. Oh, okay. I didn't know we could see it during the day. Yes, we can. So, yeah. So the story that's been related by Stefan is that one of the observers for Pan-STARRS used to work at an observatory in Russia, and the Russian Air Force called them trying to figure out what this unidentified flying object was, and what they had identified was Venus. So the Russian Air Force was about to scramble to go intercept Venus. Why didn't they just say, "Go for it"? Yeah. Yes. Yeah. So, yeah, the question is that the very thick atmosphere on Venus has led to this runaway greenhouse effect. And have they used that to calculate or to figure out what possibly could happen here with the greenhouse effect here? To a large extent, yes. If we did not have an atmosphere, if we didn't have water vapor in our atmosphere, and what's the number one greenhouse gas? Water vapor. Number one greenhouse gas, water vapor, not carbon dioxide, water vapor. If we did not have the water vapor, the greenhouse effect from the water vapor, we'd actually kind of be somewhere around freezing right now. Okay? So the greenhouse effect, there's some good to it, but that does not mean we want to push it any further. So we've done some calculations like that, but the carbon dioxide one is a very difficult calculation, and yeah. The spectral lines are different. The question is what makes it difficult. I think it's that the spectral lines are different. And the way they're doing it, my understanding of the way they're doing it, and I'm certainly not an expert, so don't quote me on this. My understanding of what they're doing is they're looking at the temperature of the Earth and kind of getting it from that. But I could be wrong. So it's sort of a correlation with that. Yes? The question is, how hot is it on the surface of Venus in Fahrenheit? I don't know right off.
I heard 900.
For 900, yeah, it's hot enough. Hot enough, I think lead boils just barely. Yeah, go ahead.
You mentioned that water vapor is the number one greenhouse gas.
Mm-hmm.
Is there a percentage-wise that you're aware of, like what the percentage of water vapor is greenhouse gas, carbon dioxide?
So I mentioned that water is the number one greenhouse gas. The question is, what is sort of like the ratio or the fraction that is of greenhouse warming that is due to water vapor compared to carbon dioxide? I don't know that right off. So about 2 orders of magnitude stronger. So a factor of about 100 times. Water is about 100 times stronger than carbon dioxide as a greenhouse gas. Oh. Well, yeah, but what's the strength? Do you know? I don't know either. Okay, so we don't know the relative strength of carbon dioxide and water. I just know that water is stronger, has a stronger greenhouse effect than the carbon dioxide. Okay, so there's the phases of Venus. Okay. Hello. So Jupiter. Okay, Jupiter is, I love this. My image browser isn't even open, and here's Steve Cherowich commenting on my photo. Hey Steve, I wonder if you're watching the live streaming? Thank you, Windows 10. Still much better than Windows 8. Oh, Windows, I hated Windows 8. Anyway, Jupiter, largest planet in the solar system. It's about 317 times as much mass as the Earth. It's about 10 to 11 times the diameter of the Earth. Oh, hey, typo. Has anyone else seen other typos? Okay. Asphalt. Okay. Okay. Times, yeah, times, okay. Times the diameter of the Earth. Okay, so I've got a couple of typos in here. That's always good. Because I missed all my mistakes on my intro, right? I got my intro right for once. Yes, sir. So the question is the giant red spot on Jupiter a tornado or a hurricane or something? We'll get to that in the next slide. Thank you. Okay, so this is Jupiter. This is sort of true color-ish. Again, it's very difficult to get color. This was taken with the Falk's Telescope North by the Maui Astronomy Club. Kind of a cool club you have to join if you're out here. And of course, Falk's Telescope North is too large to be pointing at planets, so don't do that. Yes, I'm bad. Okay, so and one other thing about Jupiter, when this image was taken, it was November of 2011. So we've got 11. We got 11. The declination was 11, 11, 11. Thus, yeah, the declination is like the latitude in the sky. Okay, so the declination was 11 hours, 11 minutes, 11 seconds. Thus proving that Jupiter is the loudest planet in the solar system. Because it goes up to 11. Okay, so. Younger kids, don't worry about it. That was, yeah, you didn't miss much. Thanks. Okay, so, and 11 times the diameter of the Earth. Okay, so it's made of hydrogen, and hydrogen compounds, helium, and we think there's a rocky core, kind of a chewy core that you can, yeah. But basically, it's got a core that is very similar to the Earth, maybe a few times as much mass as the Earth. All right, so, and here's the Earth to scale. So yeah, got that? Earth to scale with Jupiter. Okay. Jupiter sometimes is referred to as a failed star. It would have to be about 80 times as much mass to become a star. And it's also about 5 times as far away from the sun as the Earth is from the sun. Okay? One of the cool things about Jupiter is these moons. These are the Galilean moons. This moon here comes out nice and clear. You'll notice that there's some chromatic aberrations. The left edge of Jupiter is kind of blue. The right edge is green. And then you come over to here on this moon, and you've got basically 3 rainbow dots. And here's this one moon that is happy, and it's white. What I did is I was centering. We take 3 images. We take a red, a green, and a blue image. And we center it. We center all 3 of them on some feature, and I centered it on this moon. So this moon actually moved enough that you can see its orbit. And in fact, this moon moved enough that you can see the effects of the orbit on Jupiter. Okay. So the giant spot of Jupiter, here you go. Right there. There you go. All right. This was actually, the reason this is black and white is this is a single image. It was taken with a hydrogen alpha filter. I did that so we could get good contrast, and hey, it worked pretty well. This was taken by a couple of students over at Kinkekalike. They were over here and had some time and on the telescope, and so, if you like airplanes, you hang out at an airport. Pretty soon someone's going to say, hey, you want to go up flying in an airplane? You like telescopes, you hang out with astronomers, all right? It's the largest hurricane in the solar system. You're exactly right. It is what is called an anticyclonic storm. So a cyclonic storm is one that you have like a low pressure drawing air in, and then the Coriolis force causes it to spin left or right, spin clockwise or counterclockwise. Anticyclonic, basically the flow is outward, and so Coriolis force has it spinning the other direction, and so that's it's gas flowing outward, and it's known to have lasted for at least 186 years, perhaps as long as 351 years. Okay. Saturn. If anyone needs to go. You can go. We've been over an hour here, but I've got loads more slides if you want to stick around. I told you this is just like someone's vacation slides, isn't it? Yeah. So Jupiter, yes, the hostel, you would love it. We stayed at this little quaint bed and breakfast. Okay. So Saturn is about 95 times the mass of the Earth. So we'll get to that, and it's about 8 to 9 times the diameter of the Earth. So it has half as much volume as Jupiter, and 1/3 the mass. So in other words, it's not as dense. The gravity is not as strong, and so it doesn't pull the planet together as much, and it doesn't get as dense. Which is interesting, because then if you think about adding a little more hydrogen, you're not getting as much planet growth, and eventually you get to a point where you stop growing, and you add more hydrogen, the planet gets smaller and smaller. Jupiter is pretty close to that limit. Okay. Saturn also is made of hydrogen compounds, helium, and this crunchy core. Okay, this rocky core. There's like iron in there and silicates and everything you find here on the Earth. It's about 10 times as far as from the sun as the Earth, and the biggest feature is the rings. When you look through a telescope at Saturn, you see the rings. That's the first thing everyone notices. Then they go around to the front of the telescope to look and see what you've stuck in front of the telescope, fool them, and then they go, oh, that's real. We've actually watched people do exactly that. It's kind of cool. And since it's got a ring, we of course know that it's married. Okay, so rings, they're mostly water ice. Okay, so they're basically, it's snow. These are rings of snow orbiting around Saturn. There's some carbon and also some tholin compounds. These are hydrocarbons that have been struck by ultraviolet light and kind of breaks them apart and kind of gives it the brownish color. This is a bit too blue. I was trying to get the color about right. This is actually a bit blue. In the middle here, that's getting kind of close. It's kind of a brownish, to be a true color. So let's really quickly look at the solar system, kind of a map of the solar system, so you know how to get to the favorite bed and breakfast on that I've been talking to you about. Okay, the center of the solar system, there's the Sun, there's Mercury, Venus, Earth, Mars. We're going to talk about some asteroids in just a moment. Then you have Jupiter. Then we zoom out, we've got Saturn, Uranus, Neptune, and Pluto. I know why they concluded Pluto as a comet, but okay, it's a dwarf planet. I'll come that far. Okay. We're also Pluto is out here. You see, there's kind of some little flecks around there. That's what's called the Kuiper Belt. So there are a bunch of other things that are very similar to Pluto out in this belt that Pluto is part of. Okay. So here's the orbit of this one comet that they were interested in. And you can kind of see Pluto as the fuchsia in here. Okay. And then if you zoom out even farther, so that's that orbit there, here's the extent of what's called the Oort cloud. These are big chunks of ice that are orbiting the sun. This is where comets come from. These are long period comets that come from here, and short period comets come from that Kuiper belt. All right. And so the Kuiper belt is like a donut of ice chunks orbiting the sun. The Oort cloud is kind of a halo. It's three dimensions. It's three directions. It's more like a cloud, a round spherical cloud of ice chunks that are orbiting around the sun this way and that. And as we pass by some nearby star, we probably exchange ice with them. Okay. The extent of this Oort cloud, there are people, the numbers I've heard is 1/3 to 2/3 of the way to the next star. This is very extended, this cloud of things that are kind of orbiting the sun. Okay? We have not yet detected them. They start so far away from the sun that it's that the light from the sun is very faint by the time it gets out there. And then it's got to come back to us, and so it's getting fainter as it comes back to us. They're very hard to detect. And then somebody painted them all black, I'll bet, like made them all asphalt colored. Yeah, like weathered asphalt, exactly. Yeah. So the question is, are the rings around Saturn unique, or do we see them a lot of places? Saturns are unique in how strong they are, how predominant they are. But Uranus, we've known for years that Uranus has rings. Neptune, rings. Jupiter, we found rings. We're even finding rings around the Earth. A friend of mine was helped with a paper that was in Nature a couple of years ago. They found a ring around an asteroid. So rings can show up just about anywhere. Yes, all the planets are married. Yeah. See, is that why they're so far away from each other? Yes, exactly. Yeah. Pardon? How dense are the rings around Saturn? I don't know. The truth is, you would not look for a 3D density almost. You would look for a 2D density. Because if you take a sheet of paper, that's how thin the sheet of paper is compared to its other dimensions. These rings are much thinner than a sheet of paper for the same dimensions. They're just incredibly thin compared to their size. Yeah. So the question is that they sent a satellite out, and there were specific sounds coming from Saturn. Yeah. I don't know. Did you also Jupiter? Is that from radio? Okay. Yeah. So there are radio waves coming from Jupiter and Saturn, and yeah, that's maybe not terribly surprising. So those radio waves can be turned into sound that our ears can hear. And yeah, they're probably pretty interesting sounding, kind of moaning or yeah. Jupiter's much louder. Yeah, well, Jupiter has a stronger magnetic field, so that might be why. Yes, sir. Your arm's going to fall off. Mm-hmm. So the question is that he's heard that they think there's a ninth planet, not Pluto, but a ninth planet that's more like sort of like Neptune maybe. And yeah, the reason is that they see comets coming from this part of space, and comets have to be pulled into the solar system by something heavy. Let's get on to the comets, and we'll talk, and if you'll remind me when we hit comets. Mm-hmm. Okay. Yeah, I don't know what that is. So maybe you know something I don't. Okay, so if this is the galaxy, and I apologize to people here because that you can't see the disk of this this galaxy. This is actually Messier 64, black-eyed galaxy. But this is one time where the people in the virtual worlds probably have a little bit of advantage. They can see this a little better. But the Earth is about 27,000 light years from the center of the Milky Way. And the Milky Way is about 100,000 light years side to side. Just remember that, Mrs. Brown. Okay, there are some people that really do catch my references. That's scary. Okay. So, yeah. I'm glad you brought that up. The comment that was brought up was, I don't want to be in the center of the galaxy because I've heard there's a black hole there. Yeah, there's a supermassive black hole at the center of the galaxy. We'll see that in talking about galaxies. Not even light can escape from black holes. Apparently my slides are out of order too. We should have gone on to asteroids next. This is an actual image of an asteroid that was taken by the Los Cumbres observatories. Asteroids are basically the leftover building blocks of the planets. So they're bits of rock, mostly rock, about 7% iron, a little bit of ice. Think of them as snowy dirt balls is the best way to think about them. When I was about your age and your age and your age, we thought that asteroids were chunks of rock and maybe some metal in them. Now we think of them as snowy dirt balls. They're not a single, the big ones aren't even a single chunk. They're like piles of rubble, and then they've got ices that are stuck down inside them that haven't been heated up by the sun, and so that they haven't evaporated. But when we look at an asteroid, this is what we see, is this dot here, and the telescope is following the asteroid. It's keeping it in the same spot, and we're watching stars go by, and you can kind of see each image. The stars actually moved while we were taking each image, and then we read the image off, and that's where the stars kind of jump a little bit. The question is it tumbling? Is that why it's getting brighter and fainter? That was actually what Miss Barber was doing with this asteroid. She was measuring the rotation rate by seeing how it got brighter and darker. But most of the brighter and darker that you're seeing in there is probably twinkling. It's scintillation. It's from the atmosphere. Okay. Then we also have comets. These are again sort of leftover pieces from the formation of the planets, but these are further out. Okay, these are out in the Kuiper belt in the Oort cloud. And this is Comet Garrod. This was taken by the Falks Telescope North. I didn't get an image credit in there. I think this was the same students at King Kekalike that did that. But you can see there's sort of this little chunk of ice in the middle, and then a big bunch of fuzz, and then you kind of get a little bit of a tail effect there. So that's a picture of a comet. Comets are made mostly of ice. So, and ice to an astronomer is water ice, ammonia ice, and carbon dioxide, dry ice. And when they come in towards the sun, what do you think happens to that ice? It sublimes. Yeah. That's what's forming this cloud around the nucleus, and then the sun, the light from the sun pushes back the ions, and the wind pushes back the ions, the gas, and then the light from the sun actually pushes the dust back, and it'll form a kind of a curved tail that's somewhere between going away from the sun and orbiting the sun in the same path as the comet. Yes, sir?
So
About how big are comets usually? How big are rocks usually is kind of a similar question. Rocks can be small, they can be really big. Okay? The ones we see probably are, pretty big. So maybe a football size. Let's pretend that football size is where we'll start calling them comets. Okay? To be honest, there's a whole range of sizes, and I can't really give you a good answer. So let's pretend football fields. That good enough? Okay. This guy's good. He's got all the good questions. Okay. And these are these things from the Kuiper belt and the Oort cloud, and what happens is the gravity from like Jupiter pulls them into the inner solar system. All right. All right. Stars. Everyone's seen these. Has everyone seen a star? Okay. And okay, quiz from earlier. What's the closest star to the Earth? Yeah, there you go. Okay. So, stars are objects like our own sun. Now, wait a minute. I go outside, I look at a star. I think about looking at the sun. Look at the star. How far away do we have to put the sun so that it looks like a star? Pretty far away, right? Like mind-bogglingly, vastly far away. I mean, you may think it's a long way down the street to the chemist, but that's peanuts compared to how far that star's got to be away. Okay? So, stars are these things like our own sun. And near a star to the sun, anyone know what it is? Okay, we got two answers, Alpha Centauri and Proxima Centauri. The really correct answer is Proxima Centauri, but Proxima Centauri is part of a multi-star system. Is it binary or trinary? Trinary, that's right. So it's a trinary star system, and Alpha Centauri is one of those three stars. It's just right now the little tiny star that you kind of can't see too well, and besides it's too close to the bright star, so you can't tell the difference between the two of them. It's over. They're just right next to each other, and this little smaller component is closer to us. Okay, but actually, that's what? Temporarily, yes, it will orbit away from us at some point. I don't know when. I haven't looked that up. But. Okay, so more massive stars generally are bluer, and they generally are bigger. So if you go outside and you look at Orion, at one corner, you start to train your eyes to look at the colors of stars. You'll start to look at like one corner of Orion having kind of a blue star and another corner having a red star. Okay? Well, actually, that red star is a giant, so it's not bigger, but it's cooler, so it is bluer. All right? Cooler is redder, yes. Betelgeuse, yes. Okay, nobody say it again, otherwise we're going to have problems. All right. Large stars, okay, massive stars, and the definition is larger than about 7 times the mass of the sun, end their lives as supernovas. So they burn out all the fuel in the core, and they're so desperate to make energy, they start to make iron, which gives them like no energy. Iron fusion can only keep the star alive for like 1 day. And for a star that lives for 1 million years, very short life. Iron will keep it alive one day. Just not enough energy making iron. So what happens is the core suddenly collapses, and then the layers on top of it, the core collapses so fast that these upper layers just go into free fall, and they all fall down, and then they hit, rebound, and explode. Okay? And what it looks like, if you're looking at these, is it looks like there's a new star. Nova is new. So a supernova is an exploding star that looks like a big new, bright new star up in the sky. And who knows of who reportedly saw the first supernova? So the Chinese in 1054 is the answer. No. Hipparchus. This is something I learned last night as I was flipping through. Hipparchus reportedly did see a supernova, did see a nova, a new star. So he may have been the first person. The Chinese recorded in 1054, recorded this event right here. This is the Crab Nebula that exploded. And yes, it stands over here. You know, we're giving the same information, just slightly different flavors of it. Yeah, this is the Crab Nebula. This is a star that exploded. The Chinese saw it in 1054. I believe the Incas also saw it, some of the Inca civilizations. Okay, this was taken, by the way, by some students over at Kamehameha School. But I love taking pictures of the Crab Nebula. It kind of smiles and winks for you every time. It's beautiful. Okay. So this is an expanding cloud. It's a stellar, and in the center there's a stellar remnant. It's probably too faint to see in this picture. Yes. No, this nebula. So the question was, it wasn't. Yeah. Okay. The question was, when could we actually see the cloud? This was Charles Messier was in the 1700s. Yeah, and that's Messier 1. That's the first object that Charles Messier wanted to find comets. And so he would point his telescope in the sky, and he'd find something that was fuzzy, and he'd say, that could be a comet. And so he'd write down where it was. And then he'd go looking around. Next night he'd come back, and he'd find the fuzzy object and see if it moved. And he'd write down, he got a list of 110 objects that were not comets. This is object number 1 that was not a comet. So 1700s, there's when it was first detectable. Mm-hmm. Yeah, it's technically a nebula, but it's from a supernova. Kaboom. I like that. All right. And so this is the one you were talking about earlier. This is what happens to a low mass star. Low mass star means less than sort of this 7 times the mass of the sun that is a cutoff. Okay? These stars, as they get old, they expand into red giants, and the upper layers of the star boil off. They form these strong winds, and that strong wind makes a bubble around the star. And so you look at this gas, it's actually got things like oxygen and carbon in them. And you can actually see that. And then in the center, there's this white dwarf. That's a star that's died. I call these zombie stars, by the way. Yeah, because it's a star that died, but it's still shining, right? You can see right there. There's the star that died. So it's still shining. It's a zombie star. Okay. Am I wrong? Okay. And they're so cool that I just had to do another one. This is the Dumbbell Nebula. And a friend of mine, his daughter, was controlling a telescope one night. We took a picture of the Dumbbell Nebula, and she asked me what it was, and I said, "Oh, that's the Dumbbell Nebula." And she looked at me and said, "That's not very nice." It was cool. So, stars generally stars form in these huge clouds called nebulae. Okay, this is another type of nebula. Those were planetary nebula we just saw, and this is in the Great Nebula of Orion. And so this is the one I want to remember to talk about color for a moment. And you see this diffuse gas, and these stars are stars that have just formed, these ones here and here, which is why they kind of appear almost bluish tint. Yes. That I'm really glad you asked this question. So the question is, why is it that this and this and this don't collapse down and form stars, but this nebula does? Is that fair? Okay. Well, first of all, you've got the amount of mass of one star in these guys, in the planetary nebulas, and so you don't have enough mass to make a bunch of stars. Okay? This is, a couple thousand to a million, a couple thousand, 10,000 times the mass of the sun. You can form thousands of stars out of this cloud. It's also much colder. It's got more mass, so there's more gravity. And even then, we think that you need a trigger to start star formation in this cloud. You can have two of them running into each other. Supernova can compress the edge and start star formation. Or O stars can ionize the gas, and that starts a shock wave through the. Okay, that's kind of what we think. I'm actually on a paper that we were kind of looking at that. Yeah. Something's compressing the gas. All right? Yes, sir. How often does a new star get created in these star-forming regions? Is that right? The right question? Good. I think there's about something like one star a day that's formed in the Milky Way galaxy. Just in the Milky Way. I seem to remember, is that about what you're thinking? Yeah. Double check me. Don't quote me on that one. Sorry. But it's sort of, maybe a star a day in the whole galaxy. But now remember, these blue stars, they could live like 10 million years, right? Well, blue stars A and B, OAB, we're talking about, sort of a million, maybe 10 million years. And then when you get down to the little tiny red stars, those could last 100 billion years. Okay, the universe is not even that old. Okay? So these things that we've been seeing, those are generally little objects that'll be in the disk of the galaxy. And in fact, they're objects that are nearby us, because otherwise we wouldn't be able to see them. Yes, I had a typo on that page too. That entire page was a typo. Shh. Yes, there are typos in this. By this time it was 3 o'clock in the morning, okay? Okay. Globular clusters. They're these groups of stars that are orbiting the Milky Way, and they can be something like 1 million stars in one little group, one little knot. The ages of these groups of stars can be like 10 billion years, or sometimes even more. There was one I think I remember seeing that was 13 billion years old, and I was a little uncomfortable putting 13 billion years old on a star cluster. And what we think is these are the cores of galaxies that have been eaten by the Milky Way. So the disks, or the outsides of these galaxies, have been stripped away and become part of the Milky Way. And then here are these cores that remain orbiting the Milky Way. Okay. So the ages and distance of these clusters can be determined by measuring the apparent color and brightness. This is actually a student's project. I had a student that was working with me here on Maui, until he moved over to Oahu. And he wanted to determine the age and distance of a globular cluster by measuring its color and brightness. This was a student that was in 8th grade. It's kind of creepy. Yeah, it's what you guys are going to turn into. You're going to be asking about things like that pretty soon. Okay, so the idea is in this direction, this is plotting how red or blue it is. Blue is off to the left, red is off to the right. Up and down is how bright it is. Ignore the numbers because we use a magnitude system, which makes no sense. Don't ask. Up is bright, left is blue, and so you have these stars. And this is the pattern of, it's not this cluster, but it's a very similar globular cluster. And for each point, each one of these stars, we've measured how bright it is in blue, how bright it is in green, and then we've plotted how bright it is in green up and down, and the stars that are more blue to the left and more green to the right. And they form these wonderful little funky patterns. The big blue stars that would be right here, they've kind of gone away. They're over here. So that tells us the age, because the larger stars have shorter lives. They die faster. All right. And these globular clusters, like I said, there are these dots here that are orbiting the galaxy. Yeah, I think that that dot and that dot might actually be globular clusters around this other galaxy. I could be wrong. Okay. Milky Way. Everyone recognize Rob's pretty picture? Yeah. So the Milky Way is our galaxy. It's our island of stars. It's about 100,000 light years side to side. 200 billion stars. Some people are saying 400 billion stars. I went with 200 billion stars, which is good guess. There are probably experts that would be more precise on that. It's a barred spiral galaxy. A barred spiral galaxy. So you remember that galaxy? I'll show you a barred spiral in just a minute. Okay. This is another galaxy. This is M82, Messier 82, and it's an edge-on spiral galaxy. I kind of like these two pictures because you can see to me, it seems like they're fairly similar, kind of similar. So, and this is Columba Intermediate. Oh, I liked those guys. Those were fun. They were fun. All right, so this is a spiral galaxy. See how it kind of looks like a whirlpool? That's why it's called the Whirlpool Galaxy. If you were actually looking through a telescope at this galaxy, mostly what you would see would be the center. And then as your eyes got sharp and trained and well adapted, you might start seeing some haze around that. And if your eyes get really good, then you start to see these spirals. I cannot see the spirals in something like this, personally. I don't think so. You can? Yeah, so we'll stand. Okay, I'll look at those. But okay, so a barred spiral, this is kind of like our galaxy. See how there's what looks like spiral arms? And you see how in the center it's kind of a little bit bar-like? So it's a barred spiral. That's the type of galaxy we live in. Now, is this our galaxy? No. The farthest we've gotten a spacecraft from the sun is just outside of the solar system. So we haven't gotten anywhere near the outside of the galaxy. So we can't look at our galaxy and send a picture back. Oh, yeah. Hi, Pat. Thank you, Windows 10. Galaxies. So galaxies also can kind of have friends. They can hang out. They have gravity. They can hold together in groups. And this is a group of interacting galaxies called Stephan's Quintet. And the Milky Way belongs to, are you ready for the creative name? The local group of galaxies. Boy, someone must have stayed up all night thinking of that one. Okay. Yeah. Just call it the local group. I'm going to bed. Okay. Come on, the sun's up. I'm going to sleep. Okay. The local group is part of what's called the Virgo supercluster. The Virgo supercluster is part of the Laniakea supercluster.
Sounds quiet.
Yeah. Actually, it is. Yeah. Lani is sky, and Akea is large, or vast, if I recall correctly. And yeah, and this was discovered by Brent Tully, who's a researcher over on Oahu. I've actually done a little bit of work with him. But I like this picture, and this is on our calendar this year. There are clusters of galaxies, and then there kind of be these strings of galaxies or clusters of galaxies. Okay. Yes. What's the scale of that image? Yeah, okay. I can't quite read that. The Milky Way is not even a pixel in that image. Okay. I think that the dots, the points on on here, what they're mapping are actually clusters. Yeah, they might be. Those might be Abel clusters that he was working with. Okay. And then the universe. Now, the definition of the universe is all existing matter and space considered as a whole. In other words, it's the cosmos. Okay, well, wait a minute. All existing matter and space. How many of you have heard of the theory of multiverses? Multiple universes. The question was, what's multiverses? So multiple universes. And we had a guy out here by the name of Alex Filipenko talking about multiverses a few years ago. And so that means multiple universes. But if there are multiple universes, universes are made up of space, so there would only be one universe because they both exist. So I don't like this definition of universe. I would like to say it's, all the space that you could get to by moving, and all the stuff contained within that space. Because effectively, we could go to a rocket ship. We could go anywhere in the universe. And that would still allow us to have other universes. I don't know. Maybe it's just me. I mean, I'm just cranky. Our universe, we think, is about 13.8 billion years old. Okay? And it's made of, oh, look, 75% hydrogen, 25% helium. At least that's what it was made of when it originally was born. We do have stars that make other elements, and such as our carbon and silicon. So anything that isn't hydrogen and isn't helium had to be processed in a star. It had to be turned into whatever it is. Only hydrogen and helium existed in the beginning of the universe. So so I hope you all know that you're made of stardust, quite literally. Yeah, Carl Sagan. All right. Now we could talk about the fact that parallel lines in the universe diverge and other fun things like that, but I probably have bored you to tears. I'm surprised that anyone's still left. So finally at the end, thank you. All right.
You guys need more comfy chairs.
Yeah.
Anything planned for the transit of Mercury?
Is anything planned for the transit of Mercury in May? That's the 20th, is it? Yeah, I just noticed it the other day. I don't know of anything planned yet, but we might do something. Yeah. Other questions? Yes.
When measuring mass and, space and all this stuff, but how do you know about sound? Is there anything in this universe that humans hear sound? Like we can hear volcanoes going off.
Okay, how do you know about sound?
Sound from
So,
bombardments and collisions.
well, sound has to have something like air or water, it has to have a medium to travel through. So for us to have sound, there has to be, probably you have to be in something like an atmosphere. So in space, there's not enough stuff to really carry sound. Yeah. Yes, all these things are happening, but they're quiet because you're in space. There's no sound in space. Yeah. Yeah.
Nobody can hear you scream. Yep, that's the expression.
Let me, pardon me. Let me through here. Yes.
Next time, are we going to talk about the Big Bang?
You want to talk about the Big Bang? I think we might. I think Alex Filipenko may have given that talk. You could watch on our archives.
Oh.
Okay.
I read a new theory about the Big Bang that there's a 4-dimension black hole.
Oh, that the universe could be part of a black hole. The whole universe could.
Shell around the black hole. I read something about that in a magazine in Scientific American.
I want you to keep reading. I like what you read.